This is a screencast to substitute for lecture on Monday, September 23rd, and this is the second part. In this part, I'm going to talk about antiderivatives of power functions and polynomials. The motivation here is so that we can start thinking about sketching a function f of x if we're given its derivative f prime of x, and that's a graphical version of taking an antiderivative. And I'm also going to talk about tangent lines. So antiderivatives, which are effectively going backwards through the derivative process. If you're given a function that is the derivative of some f of x, so in other words we're given f prime, in this case 6x squared plus 4x minus 1, then one of the four of these should be the antiderivative, and I want you to take a few seconds, stop the video if you want, and figure out which one is your choice answer. Okay, so I trust that you've taken a few minutes to commit to an answer here, so I'll flip the next slide here to show the answer, and in fact there's three perfectly reasonable answers. The first two are specific functions, and they happen to differ by a vertical shift of 2. You'll notice we've just added plus 2 to the 2x cubed plus 2x squared minus x, and then here we have a plus 2. In the third, or the fourth one here, the third one that I've marked as correct, we've got a plus c, which is kind of arbitrary. Now, you could say that this third one is the best of them because it captures all the possible antiderivatives. But these are possible antiderivatives as well, and so they're not really incorrect. It's just that I would say this one down here with the plus c is the best one, or the most complete one. All right, so basically the difference between them is just a vertical shift. Why is that important? Because if you're given the derivative of a function, that's specifying just the slopes. So we know what the slope has to be everywhere, but you can have three different functions like this one here. So this one here might be b, this one might be c, and this is one example of d with a particular value of c. And you'll notice that the slope at every value of x for each of these three functions is exactly the same, and that's because vertical shifts do not change the shape of a function, they just change its position. Okay, so here I'd like you to take a few minutes and draw f of x given this f prime of x. And what we're doing here is we're dealing with a piecewise linear function, and what you need to do is think about taking the antiderivative and draw the antiderivative, meaning f of x, for each of the series of linear pieces. Okay, so I trust you've now taken a few minutes to do that, and I will go through it. So first thing I'm going to do is I'm going to draw a new axis, and now we can start breaking it up into pieces corresponding to each of the pieces of the f prime above. And so the easiest three pieces are these ones here, A, B, and C. And the reason those are easy is that these are regions where the function has a constant slope. Now, when the derivative is constant, these are regions where f prime is constant, which means that f has a constant slope. And a function with a constant slope just means that at every value of x in that interval, the slope has to be the same, and what we get is a straight line. So what that means is we can, if we knew what this value was here, we'd be able to draw a line with that slope. And I'll just pretend I know what it is, like that. And then in the middle one, you see now in region B, we see that it's now a negative, so we have a straight line with a negative slope, and it's actually about the same value below the axis as the other one was above, so that tells us that this should have a negative slope of about the same inclination. Okay, so I've placed them in arbitrarily high relative to each other. I don't know exactly where these are going to end up going, but I'm just sketching them out for now. Finally, the third easy one to draw is the C region, and there you can see it's a positive slope of a slightly lower steepness than the first one we drew. So I'm going to draw that one with a slightly lower slope. Okay, so let me now just fill those in with those three and get rid of those. And now we have to fill in the in-between pieces. So let's say part D and part E. So in part D, we see that the slope starts off just as steep. So you'll notice whatever the steepness was up here, it starts off being a similar steepness. So if this line we got over here represented that first piece, now the next piece is going to start with a similar slope, but what happens as you increase the value of x, the slope decreases until it actually hits 0 at this point here, and then it starts to go negative, steeper and steeper. And so what we find then is that there's some kind of a cap in it. Now you'll notice that the slope goes from that value all the way down to that value. The function, the derivative of the function is smooth, so that means that the function itself must be continuous, because if there was a jump at these breakpoints in the function itself, then the derivative would not be defined. And if you look closely at all these spots here, for example, and here, and down here, here, those two meet up and there's no empty circle, except for the empty circles I just drew, of course. So let's get rid of those so they're not deceptive. And what that means is that the slope here is the same and it's got to meet up and be the same there. But here I've got jumps. If there are jumps in the function, then that would mean that the derivative is not defined. So I'm actually just doing this to get the shape kind of right. And now what I'll do is put those in and get rid of these two. And now I can't have those jumps in there, because if this were the function, then the slope would be constant, and then the slope would kind of go infinitely steep, and then it would go back to being some finite value. And that's not what the graph shows. And so we're going to rearrange these. Oh yes, first let me just point that out. So here's a maximum here, which corresponds to this 0 here, and there's a minimum there, which corresponds to this minimum here. And then we're going to be able to slide these around and then link them up, because we know the function has to be continuous to make this nice smooth curve. Now this is a linear piece. This has to be a quadratic piece because its derivative is linear. And another linear piece, and then another quadratic piece, and finally a linear piece. Okay, so that's how we draw. Certainly for piecewise linear ones, this is how we would draw it. Now the same idea would apply if we had more complicated shapes, but at least in this case we know that the pieces are linear and quadratic because the derivative pieces are all constant or linear. Now the function that I've drawn here is only correct up to a vertical shift, so I can slide the whole thing down and I would still have the same f prime, but the shape is the same. So what we're targeting here is getting the shape correct, and then the vertical shift is kind of arbitrary. Okay, so a natural place where polynomial antiderivatives come up is in position velocity acceleration relationships. So if x of t is the position of some object that is a function of time, then the velocity will be the rate of change of position, which is x prime, and we call that v of t. And the rate of change of the velocity is what we call the acceleration, so we'll call v prime a of t, and that's actually the second derivative of x of t. So there's a special case, constant acceleration. So if you are talking about throwing a ball on planet Earth, on the surface of planet Earth, so we're throwing balls up here. Now this radius is huge, it's like thousands of kilometers, and the height of a ball that's typically thrown is certainly, maybe 1,000 times smaller. So the extent to which the distance here from the center of mass of the Earth is changing is very minimal. If you were to go and throw a ball way out into the outer atmosphere, or even beyond that, then we'd find that gravity actually changes because we're getting further away from the center of the planet. But if that's not the case, then we can get away with this assumption of constant acceleration. In other words, the effect of gravity just in this region down here is fairly constant, and that's creating a constant acceleration. So what happens when you have a constant acceleration? You have a v of t that's equal to the antiderivative of acceleration, and that is just constant. So we have an at plus some arbitrary constant. Now, in the case of throwing balls into the air, we might know how quickly the ball is moving when we first launch it, so we can plug in v of 0. If we put in v of 0, then we get a times 0, which is 0 plus c. So c is equal to the v of 0, in other words, the initial velocity. So we replace c with this more meaningful name v sub 0, or what we call v naught. Okay, so now we can repeat this process and look for x of t, the position of the object that's undergoing constant acceleration, and the antiderivative of a times t will be, now let me get rid of these. So the antiderivative of a times t will be quadratic, and in particular it'll be one that has at as its derivative, so this is going to have to be something of this form. And the reason we have to put the half in front here is because the power law says that when we take the derivative, this 2 comes down in front, and the 2's have to cancel, and we lose a power here, and the 2's that would come down in front would cancel, and we'd be left with just at. So now what we have is x of t is going to be a half of a times t squared, that's the half that I just had in that previous line there, plus v naught, when I take an antiderivative, just becomes v naught t, and I have a new arbitrary constant in front, or at the end of that expression. Now, same as before, x of 0 is going to be, well, I have a 0 there and a 0 there, and so all I'm left with is d. So d, I can rename that in a convenient way. In particular, I'm going to call it x naught. So there is the x naught at the end. And this is a general expression for x of t when the acceleration is constant. And this is sort of a classic area of introductory physics, which is called projectile motion. Balls falling or being thrown near the surface of the Earth.